Okay, children, welcome back to the online tutor. Today, I'm going to represent a permutation and combination second tutorial. So, the previous tutorial we have discussed about the permutation, what is a permutation, and what are the permutation theorems that we have, right? All. So, this is about the permutation. So, we discussed this one, and we didn't discuss the combination. Then the theorem one we also discussed the thing should be different, and this theorem number 2 also we discussed. This is about this equal things theorem. So today we have the third theorem. So this is the last theorem we have under the permutation. The arrangement which can be made by taking r things out of n things is NPR. So NPR equal factorial n over factorial whole thing n minus r, right? Not for the r, n minus r. So the note also available, all things should be different. If we are using all n things at a time, then use the theorem number 1, right? So this is the third theorem. So the third theorem is NPR. So the NPR normally known as a permutation operation, right? So this is the actually permutation theorem operation, right? The previous theorems we discussed about some different scenarios, but it was not about the permutation, the main one. So this is the main theorem, right? So the second theorem, it was the number of ways in the which n things may be arranged among themselves, right? So it was factorial n over p q r divided by. So that case we discuss about the same things repeating, right? Repeating case. But the theorem number 3 we discuss about the NPR case, right? Let's look at the board. So you can see we have n number of elements, but we are using only r at a time, right? But we have total n number of elements, but we are using r number of elements. N is always greater than or equal r, right? So that the total permutation, right, the total arrangement is NPR, because we are using r number of elements, right? It's n minus r divided. So this is the the arrangement of using r number of elements. So assume we have r number of spaces, and but here the n number of elements are available, right? We can put n number of elements, but the available space is r, right? So we have to select only r elements. So like assume we have so assume the number plate case, right? The number plate we have only four spaces, no, but there are 9 numbers suitable for put in that space, right? So the likewise. So actually this theorem is the previous theorems we put all n numbers, right? But here we are using only r number of elements. That's the difference, right? Let's derive this theorem number 1 using this theorem number 3, right? So the theorem number 1, we have n number of spaces and n number of elements available, right? So the permutation is npn, right? So because we are using all npn, so this is n, because 0 factorial is 1, no? Then the answer is factorial. So you can see we can prove the first theorem as well using our third. So the main one is third, but the other important thing is we can't derive the second theorem using the third theorem, because the second theorem we using the second theorem we have same elements, but here we are all things should be different, right? All things should be different. If you are using all n things at a time, then use theorem number 1. So that was theorem number 1, but the note number 1 is all things should be different. So that is the case why we are not using prove the second theorem using the third theorem, right? So this is the second theorem, right? Here PQR are same, right? Okay, so let's move to the example. Find how many numbers between 2000 to 3000 can be formed using a digit 1, 2, 3, 4, 5, 6 if repeating of digits are not allowed. So you can't use the same letter twice, right? Twice or thrice or anything, but only one letter occurring one time. So we need to find the number of chances, right? 1 2 3 4 5 6. These are the elements that they given to us, and we have to prepare 2000 in between 2000 to 3000. So therefore we have 4 spaces, and so n is 6, no, r is 4, because there are 4 spaces available. So we have to arrange it to the straight line, right? So you can see we have 2000 to 3000. So how to put? So the first element always should be 2, no, because otherwise it's not under the 2000 to 3000. So all three we have 6 elements, right? 6p and 3 are suitable for, sorry, so I just forget. So we have 5, no, 2 already put in. So 5p 3, because 3 is suitable for put into the space, right? So we can write 1p1 for the 2, and the other one is 5p3. So 1p1 is 1, the 5p3 is 5 over 2, right? Factorial. So 5 for 3 2 1 and 2 1, so 2 cancelled, and the answer is 60, right? So that is the answer of the first question. So we have 60 number of different arrangement using these 6 elements, right? The second question: how many different numbers with 3 digit can be made from the digit 2 3 5 6 7 9 if each digit is used? The first round number is the number less than 400. So how many different number of with 3 digits? So we have to, so actually now the r is 3, no, the n is 6, the number less than 400. Okay, so 2 3 5 6 7 9, these are the elements, and also we have 3 spaces. So n is 6, 6p3, factorial 6, factorial 3, which is 6 5 4, factorial 3 cancel. Answer is 120, right? So this is the arrangement, the total arrangement, right? How many different number of digits can be formed? The number less than 400. So let's move to the first row number. 400 mean we can put 2 3, only 2 and 3, right? Only 2 and 3. Others suitable, others are 5p2 and again 5p2. So 2 3 and fix 5p2 twice, 5 2 into 2 and 5 40. So this first row number is 40, less than 400 case, right? Right. Let's move to the next one. The number is even. The number is even mean so the last number should be 2 6, only 2 and 6, right? So the last number should be even, 2 or 6. Others can be again the same thing, no, 5p2 5p2, right? 5p2 is the total number of arrangement, 5p2 into 2. It's again 40, like a previous one. So this is row number 1. The next number, the number is, sorry, this is row number 2. The number is odd now. So number is odd mean, yeah, you can write the total arrangement. So the very first case we have 120, now it's 40. So you can subtract the even cases under the total case, right? So because if the number is not even, that means it's odd, no, then 120 minus 40. Or else you can use the same thing, 5p2 into 2 case as well, because you can put 3 5 7 9 for the 5p2 is occurring 4 times, right? Because 3 is fixed, 5 fixed, 7 fixed, 9 fixed, likewise. Next row number, the number is divisible by 5. So the number is divisible by 5 mean you can put only 5, no, because 0 is not there, and we can put only 5. 5 is divisible by 5, no, the last number. So the other case is 5p2, right? 5p2 is 20. Right. This is the question, the second question under the theorem number 3. So I think you might have a small idea about the permutation. Doesn't matter, we can carry on. Let's move to the next example. Using 7 constant and 4 vowels, how many combinations can be made by only using 3 constants and 2 vowels at a time? So 3 consonant and 2 vowels, right? So we have 7 consonants and we have to use 3, and 4 vowels we have to use 2, and 7p3 is suitable as a consonant and 4p2 is suitable for the vowel. So the answer is the multiplication of the both. Right. So the next number, the number plates are made by RMB using 2 letters from the alphabet and 3 numbers using 1 to 9. How many number plates that they can be arranged? Right. So 2 letters, right? So 2 letters mean we have 25 alphabet. No, 25. The other one is we have 3 spaces, right? 1 to 9 is suitable, right? So 25p2 as a the total number of arrangement, 25p2 as a English letter, and 9p3 as a number, right? So the number, this is actually old one, right? A 8 flag signal consists of running up 8 flags on a vertical pole. Determines a signal. How many different 8 flag signal can be made with the first row number? The flags are from the different 8 flags. The flags are from different 9 flags. So we have 8. We have to make a 8 flag signal, right? To use a 8 flag signal, right? So here so how many flags that we have? We have 8 flags, right? And we have to use all flags, right? All flags, it's factorial 8, no, under the first theorem. So or else 8p8, we are using all flags. So the next one is the flags are from different 9 flags. So now we have 9 different flags, but we are using only 8. So this is under the third theorem, right? 9p8. Simple. So the next row number, 4 identical red flags, 2 identical blue flags, and 2 identical green flags. So we have to summarize it: 4 red, 2 blue, and 2 green. 4 red, 2 blues, and 2 greens. So total number is 8. Right. This is the total number of flags with the colors. So what they ask for, I think 2 black, right? So how to put it? So this is under the second theorem now, because red and we have red, 4 blue, right? Total number of arrangements, it's factorial 8 divided by the same thing, right? 4 2 2, right? Because we are in second theorem, we are always divided by the same thing, no? Same occurring cases, right? So next row number 4, 4 identical red flags, 3 identical blue flags, 4 identical red flags, 3 identical blue, and 2 identical green, right? So total number is 9. But we are using 8 flag signal, right? So the case now we have 9 flags, but we have to use 8. The thing is which flag should be removed, right? It can be red, it can be blue, it can be green. So the thing is we have to write one by one, right? Removing red, removing blue, removing green. So the red one is removed, the blue one is removed, and the green one is removed separately. Okay, so when we are removing, so this is the ignore color, right? So we have now red, no? So we removed one. So the red was removed, mean we have only 3 red, no? Others are same 3 and 2. And the blue one is removed, mean is 8, 4 and 2 and again 2. So the next one is green one is removed, 8 factorial. So the normally red is 4 and blue also 3 and the other is 1 because one green is removed, 8, right? So these are the situations that we are using 8 flags under the 9 flags, right? So the 280 is the first one, so you have to simplify it, right? I'm directly writing the answer, 420 and 560, right? So the whole process is this total, right? The 8 flag signal 280, 420, 560 total. $1,260. This is the total number of arrangement using 8 flags, right, under the 9 flags, right? So this is a little bit different, but in these questions we are not using third theorem actually. This is under the second theorem, no? The thing is we have 9 flags, but we have to use only 8 flags, right? So we have to ignore one by one, red, blue, green, respectively, and we found the total number for each category and we added it. That's all, right? Okay, so now I'm going to discuss one more important thing. This is taken from a textbook, right? Find the permutation of ABC. All 3 are arrangement, right? So the first one, the possible arrangements of using all ABC, right? Find the permutation of ABC, no? So this is the way of writing, right? So first we write ABC and ACB, BAC likewise, right? BCA likewise. We have 8, 1, 2, 3, 4, 5, 6, right? 6 number of way of writing the first Rome number. So the second Rome number, what they ask what is the, using the formula of find the permutation of ABC if only 2 are in the arrangement. So we are using only 2, mean AB, AC, BA, BC, CA, CB. So likewise we have again 6 number of arrangement, right? So when we are using the third theorem, so the second one answer is 3p2, right? 3p2 means 6. So the first Rome number, which is factorial 3, it's under the first theorem, right? So answers are same, answers are equal. So actually in the using theorem is very easy. Instead of writing this all, right? So I'm taking this example to represent why we are using the theorem. So the advantage of using theorem, right? Let's move to the next example. A signalman has 6 flags, of which 1 is blue, 2 are white and the rest are red. He reads the message by hoisting flags on a flagpole. The message being conveyed by the order in which the flags are arranged, which is the number of different messages he can send by using all 6 flags, by using exactly 5 flags, right? So we have 6 flags now. the colors also given, right? So first of all we have to summarize it. 1 blue, 2 white, 3 red. The total number is 6. So the first round number, they are using all 6 number of flags, right? So which is factorial 6 divided by factorial 1, factorial 2, factorial 3. Under the second theorem, no, this is easy. So the next one, by using exactly 5 flags. Using exactly 5 flags means like the previous one, right? So we can ignore blue, we can ignore white, we can ignore red, right, separately. So you have to write one by one, removing it, right? So only 5 flag signal under the 6 flags, right? So I'm first I'm removing blue R3 and white 2. The second thing is removing white and red 3, white 1 and blue 1. And the other way is removing red, no, R2, white 2 and blue 1, right? So actually this is the only way of removing one by one, right? So the first one is 5 factorial divided by 2 and 3. So the next one is 5 factorial divided by 3 and 1. So next one 5 factorial divided by 2, again 2. So the like the previous signal case, no, the signal case from number 4, ne? So we have to add these 3. The first 10, 20 and the next one is 30. So we have to add all. 10, 20, 30, it's 60, right? The total number of arrangement using 5 flags, right? Using only 5 flags under the 6 flags is 60. So 60 total arrangement, right? So this is about the permutation combination second tutorial. I think you might have idea about the permutation now. So we didn't discuss about the combination. It's a separate part, but both permutation and combinations are connected. So the next tutorial you will understand what is the combination is. And so I'm also again recall the permutation theorems and all, right? This is theorem number 1 and this is theorem number 2, this is theorem number 3, right? And you have to go through again, right? And these are the homeworks that I have put. So once I expect you to write the note, and after that do the exercise that I have discussed in the tutorial, and after that you can do the homeworks as well. So this is actually easy lesson, right? So this is under theorems, right? So once you have learned it, you have to memorize the theorems, and you can recall the theorems, and you can use it, right? Okay, these are the homeworks. You can try yourself. Okay, so thank you very much for being with us. Section is available. You can write any comment. Thank you very much for participating in this tutorial. So the third tutorial I will discuss the combination. Okay, so I added a small video, right? So this is video. So this is, the permutation combination is highly practical subject, right? So highly practical mean in lottery cases they are always using the permutation theories, right? Because they have lottery and they put at numbers. No, the numbers is put in the permutation way. So each lottery, they know how much they should be spent as a price, right? As a price, and so they allocate the total price, and the other rest of the money is their profit. So this small video describe you how to do this kind of lottery, right? Thank you very much for participating, and have a good day.
And it showed. He spent every minute he had off work and family life analyzing papers on math and working on his own algorithm. And finally, after several years, it was ready. Mandel called the result of his research combinatorial condensation. He didn't want to disclose the method, but he claimed that, in a lottery with 6 total winning numbers, he could accurately predict 5 of them. That brought the probability of winning the lottery from 1 in several million to 1 in several thousand. A drastic drop, don't you agree? Using his algorithm and having gained support of his friends and relatives, Mandel managed to buy huge quantities of tickets with numbers that were most likely to win. And the risk paid off. He won the first prize, which was about $19,000, paid off his debts to everyone who helped him, and still benefited quite a lot. His net profit was $4,000, enough to start a new life. And that's exactly what he did. Mandel packed his family stuff and went to Western Europe, where he moved from place to place for 4 years. Such a lifestyle is tiring when you're not alone, though he finally settled in Australia. Quite a far cry from Europe, huh? There, he decided to continue his research into the lottery business and succeeded. You see, when he earned his Australian citizenship, he got access to every Commonwealth resource available for anyone with this status. And that meant he could take part in the UK lottery system, which happened to be much less complicated than the Romanian one he cracked before. So he sat down, took a good long look at the system, and after some time got an idea. Mandel realized that, in order to win every time, he only needed to buy all the number combinations there were. Sounds crazy, I know, but even so, he made it work with a very deliberate solution. His plan included 6 steps. First, he would calculate the total number of combinations possible in any given lottery. For example, one where he had to pick 6 numbers from 1 to 40 would have 3,838,380 combinations. Yeah, count them yourself if you don't believe me. Second, he would find lotteries where the jackpot was at least 3 times as big as the number of combinations. This was a requirement because otherwise he would either win nothing at all or even lose money. You'll see why in a few moments. Third, he'd raise money to buy every single combination. This was the toughest part of all. He would convince people his method worked and persuade them to sponsor his venture by buying as many lottery tickets as they could afford and sending them to him. He promised to share the winnings among the investors and himself. So after a while, his ideas got popular enough to attract hundreds of backers willing to win some part of the jackpot. Fourth, he would print out literally millions of tickets. Doing this, he ensured that every possible winning combination would be somewhere among those millions. And that, in its turn, made Mandel a multiple winner of every lottery there was. Not only did he win the jackpot, but he also took the second, third, and other minor prizes. Fifth, having printed out the tickets, he would deliver them to the official dealers. They had no choice but to accept the tons of paper Mandel hauled to them, because, however crazy it sounds, the whole operation was legal. The British Commonwealth and Australian authorities just couldn't believe anyone would be so bold as to do something like this. Stefan Mandel was one of a kind, and he probably knew it himself. And finally, the 6th step was to take the prize. And this one is exactly why he needed the jackpot to be 3 times the number of possible combinations. You see, after winning, Mandel had to pay his investors their due. That meant the more backers he had and the more they paid, the more money he had to cough up after winning the lottery. But that wasn't all, since Mandel also had other costs to pay, including printing and logistics, so eventually he would be left with not a very astonishing sum on his hands. If the jackpot had been smaller, he would have probably found himself with less money than he had before the whole affair, hence the prize amount. The plan was incredibly simple, come to think of it, but at the same time it needed a lot of effort. Stefan Mandel worked day and night to make it come true, and over the years he succeeded in creating what he called a lotto syndicate. A network of hundreds of investors who believed in his method and were more than willing to help. With the 1980s came the computer era, and Mandel was more than happy to embrace new technology. He bought several computers and a dozen printers that ran on an algorithm he created, and filling out the combinations became easy peasy. By the end of the decade, he and his syndicate managed to win 12 lotteries across Australia and the UK. But such a scheme couldn't have gone unnoticed. Although perfectly legal, it bothered the authorities that one person could perform such a trick. So the lottery laws were changed twice in Australia. First, they prohibited printing tickets at home. Now you had to buy them firsthand from a store, and then banned purchasing them in bulk. That made Mandel look to the West. Despite his many successes, they brought modest amounts of money. What Mandel wanted now was to make headlines all over the world, so he set his sights on the Virginia lottery in the U.S. It was 1992, and the jackpot was more than 3 times larger than the number of combinations, 27 million against approximately 7 million tickets. It was exactly what he needed. Given credit for his previous achievements, he quickly gained support of over 2,500 investors, each of them paying about $3,000 to bulk purchase all the combinations. Then he printed all those tickets at his base of operations back in Sydney and shipped the bulk to the US. That's where the big game started. Hired couriers worked tirelessly all around the state, paying for tickets at stores in cashier's checks worth $10,000 each. They were short on time, but that wasn't the big trouble. The one that made Mandel bite on his nails was that just hours before the deadline for entry, one of the stores that bought tickets in bulk became overwhelmed and stopped its operation. As a result, out of 7.1 million tickets bought by Mandel's syndicate, only 5.5 million were processed, leaving too much to chance. There was nothing he could do to ensure his victory, and he only had to hope none of those missing 1.6 million combinations were winning. On February 15, 1992, the moment of truth came, the final draw on live television. Mandel's team were frantically rifling through the combinations to see whether one of them was the winner. And at last, a triumphant cry: they'd won. The Lotto Syndicate hit not only the jackpot, but also the second and third prizes, along with dozens of minor ones, their overall winnings amounting to about $30 million. It was the greatest victory of Mandel's venture yet, and it did make international headlines just like he wanted. But, as we know all too well, money spoils. While Stefan Mandel himself became a millionaire, his investors received only a meager compensation for what they had spent. And they couldn't even sue him for not carrying out his obligations, because technically he did. On a larger scale, Mandel's actions caused the U.S. authorities to change the lottery rules so no one would ever repeat his stunt. That made him the first and last person. He didn't really stop pursuing his elf. Let me know down in the comments. If you learned something new today, then give this video a like and share it with your friends.